I'll introduce myself, then Tommy, and then I'm going to do something that's probably unique for a workshop. I'm going to ask everybody in the audience to introduce themselves and tell their role. It's not a very big crowd, and the goal was to be a bit more interactive, so we'll start off a little different. Tommy.
Hi, I'm Tommy Maynard. I'm Director of Advanced Computing Systems at the Texas Advanced Computing Center. I'm also Chief Systems Engineer for the Frontera and Stampede II systems that are funded by the NSF.
Tommy, thank you very much for giving the first talk of the day. Eric?
Hi, my name is Eric Enquist. I'm the Director of the Center for Research Computing here at Rice. So we're the group that supports for the research computing activities at the university.
Hi, my name is Sanjay Sood. I am a staff geophysicist with a small nonprofit based in Minnesota. Thank you.
I'm David Baldwin. I'm with Shell. I'm the Subsurface and Wells High Performance Computing and Technical Infrastructure Renewal Manager. But really, it means I'm the Chief Architect or the Program Manager for HPC.
I'm Ricardo Millán. I am HPC System Administrator in CGG.
Kent Blancett with BP, Team Lead for the HPC Platforms Group.
Jonathan Eichelberger, BP, Platform Engineer.
Patrick Wigger, Platform Engineer at Numerical Algorithms Group at BP.
I'm Jeremy First with BP. I'm a computational scientist.
Jeremy Singer with ExxonMobil, HPC Product Manager.
Alberto Gonzalez, also with ExxonMobil with the HPC Systems team.
Good morning, Ronaldo Brooks from ExxonMobil, the HPC Systems team technical lead.
I'm Vijay Pratap. I am HPC Architect and Project Manager working for Shell Information Technology.
Hi, Anna Lanthier. I work with Vijay and David at Shell in Renewals, and I'm a Project Manager.
Greg Runsman, HPC Engineer with Shell. Also work with David and these guys and Ron.
Ron Cogswell with Shell. I'm HPC Optimization Team. We try and break what David buys.
Good morning, Emmanuel Alvarez from Total Energies. I'm Chief of Operations in HPC in France.
Hi, I'm Scott Denham at Hewlett-Packard Enterprise, a former system administrator and now a solution architect to try to figure out how we can build you guys the stuff that you need to do your job.
Well, thanks, everyone. Tommy?
All right, well, good to hear some familiar names out there. And so today I want to talk a little bit about TAC and the update that we've had over the past year. Hopefully my slides will advance here. There we go. You know, I want this to be somewhat interactive. Keith is going to try to keep an eye on. So if you do have a question during my presentation and want to ask something, feel free to jump in. Just get Keith to get to the mic because I can't hear anybody unless they speak into the microphone. So TAC is basically the research computing organized unit for the University of Texas at Austin. Our role here is really to build big production HPC systems to satisfy the research needs of the UT system and also the National Science Foundation. We started back in 2007 applying for National Science Foundation funding, and we've been very successful running the Track 2 program. And right now we're currently operating Stampede II, which is the third system in that program, third $30 million system even. And it's been in production since 2017 and been a great workhorse, very general purpose system. I have some more details on that and some updates that we've done to it recently. But again, that one's already almost 5 years of production and still getting very productive, useful life. Previously, you know, for HPC systems, about 4 years is where we kind of would normally upgrade the system, but in this case, it's still showing its legs. Frontera is currently our flagship system, and this is also an NSF-funded system. This is kind of what came out of what they call the Track 1 program, or the leadership class facilities program for NSF. It's a $60 million system. It went into production in summer of 2019, and is really targeted at the highest end users and the biggest production users. And I have more details on it, and we'll go into details on deployment, kind of design decisions we made on that guy, and recent updates and operational challenges we have on that. Lone Star 6 is our newest system. It actually went into production in December of last year. It's a brand new Dell AMD-based system. And it is our latest Rocky 8 deployment as well. And so I'll go into details of us switching from CentOS, which I'm sure some of y'all are going through now, and moving to the next releases of the Red Hat line of OSs. Stockyard 2 is kind of our site-wide Lustre storage system from DDN. It's 10 petabytes that we make available on each of our production systems. It's very useful for users when they want to run on the different systems we operate here, whether they're generating data on one system and taking it over to our visualization system, or one of our other smaller systems. It's a self-contained storage system in that it's its own basically operational system with its own InfiniBand network. And the way we connect it and mount it on all the production systems is we use LNet routers. And we route between the servers of each of the production systems. And it's nice because we can keep the storage system isolated. And so that, if a problem's happening on the InfiniBand fabric of Frontera or the OmniPath network of Stampede II, that we don't have an interruption, or it doesn't also impact the Stockyard 2 file system as well. And it's useful as well because, we put a quota on it, and users get about 1 terabyte by default, but we also make some project spaces there as well, where if there's a group of users working on a project, they can share their data in that area as well. And of course, to be able to save all this data, we do have what we call Ranch, which is our tape archive library. It's a quantum base using StoreNext as the HSM layer. And we've got about 30 petabytes of spinning disk and about 100 terabytes of tape archive capacity for that system. These are kind of our 5 biggest systems that make up the bulk of what we do here at TAC. I'm going to talk about the first 3 today, and kind of focus on the HPC side of things. But if you do have questions on the storage or anything, I'm happy to talk about that offline or anything as well. So let's talk about Frontera. So when we deployed Frontera, we ended up working with Dell and Intel, trying to determine what would be best for our general purpose use for our systems. Now, keep in mind, our user base is a very diverse crowd. You name the scientific community, and there's probably somebody running that type of application on one of our systems somewhere. So when we build a system, we can't focus on just GPUs because not all the codes that our users run are GPU enabled yet. Even though we can get some acceleration out of some applications, we can't leave everybody else behind. The other thing is, for Frontera, the goal was a capability design system. It wasn't just running a high throughput, a lot of capacity type cycles. It was designed for running the largest scale problems that can't be solved on any other systems. So when we architected it, we went with 8,000 nodes, just general CPU nodes. These are the Intel 8280 Cascade Lake processors. So we've got 56 cores per node, 192 gig of memory. That's pretty sufficient for most of our workloads. We do have a few users who may need a little bit more memory per node, but we have some high memory nodes for those cases as well. I highlighted the 396 servers. Those were not part of the original deployment of Frontera. One of the things we try to keep in mind when we design these systems is expansion. We want to make sure that we'll be able to potentially add on to the system. And in this case, once the COVID outbreak started in late 2019, early 2020, NSF told us that they wanted to allocate a large percentage of Frontera specifically for COVID research. So at the time, we were providing at least 30 to 40% of our cycles were probably doing nothing but COVID research for most of 2020. And to offset that loss in time that we focused on COVID, they provided more servers to help us be able to accommodate and still continue to support the rest of the scientific community. So, yeah, so it's been very successful. We're able to add on to it. We still even have expansion space. When we put in our core switches, the Mellanox core switches I'll talk about in a second, they weren't fully populated. So we had some spare ports to be able to grow out the system. Everything is Mellanox connected. It's HDR InfiniBand. That's pretty standard nowadays. In this case, we have DDN also providing the bulk storage. We've got 4 of the 18K exascalar storage arrays. These are using the appliance. So they do run the servers on the controllers for Lustre. That provides about 300 gigabytes a second of total bandwidth. We have carved up in a couple of different file systems. And then we have some flash servers. These are actually running IME currently, which is their DDN's burst buffer. We are exploring other things to do with these IME servers. They do work for some applications, but we think they would actually perform better with just a regular file system on them. So we're exploring other options on those as well. I did mention Stockyard 2, that's our site-wide file system. We provide 80 gigabytes of bandwidth using 16 LNet routers to the Stockyard 2 file system. And of course, you have access to the Ranch archive system. The compute nodes themselves, one of the challenges we had when we were deploying Frontera is we had a limited space in the data center. We had plenty of power available in the data center, but because of the footprint of Stampede II and the cooling we had done there, we didn't actually have that much space to squeeze in Frontera. So to solve that, we opted for very dense racks with liquid cooling to the compute nodes. And so you can see a compute node on the right-hand side there. It's got 2 sockets in it. You can see the loop of the CoolIT cooling unit there. That provides direct liquid cooling to the processors. However, the rest of the node is still air-cooled. And so what we ended up having to do for the nodes is, since there's still some heat being generated by the DIMMs, InfiniBand card, and other components on the motherboard, we do have chilled doors on the backs of the racks as well. So about 75% of the cooling is provided by the direct liquid cooling to the processors, and 25% of the cooling in the racks is provided by the chilled door. Here you can see we have 8,008 of these compute nodes. They basically have, one little SSD per node. We do put a local OS on every node. We do also leverage the integrated iDRAC management for being able to manage and monitor the nodes through our remote management servers. The 396 additional 1U nodes are identical, but except for in terms of the hardware configuration, except they're air cooled. And so we ended up putting them into some spaces where we had already the in-row cooling where Stampede 2 is located. So in terms of the compute rack, when we look at system designs and we start thinking about a system, typically we start with the building block, which is the compute node. We decide on what we want for the compute node. And then we figure out, well, how are we going to fit it into racks? What are we going to do in terms of the topology for the network? And in this case, we opted for, since we needed density, we opted for a little bit taller racks. These are 54U racks, so you do need ladders to get to the tops of the racks in a lot of cases if you need to work on it. And we designed the actual layout based on how many switch ports we had. So these are the HDR 40 port switches. We were doing split nodes, so we're using 2 nodes per port because they're only 100 gigabits to the node since they're PCI Gen 3. So it ends up that we get 44 nodes plugged into one top of rack switch and 18 uplinks. So a little bit of oversubscription. The racks are also extra deep because we also have the liquid cooling manifolds we have to put in the racks. So they tend to be pretty deep. And when you see some pictures of them, or if you've ever seen them in person, they're very, very big racks. But the good news is with the extra depth and the ability to route all the cables independently and without blocking any of the servers, it allows us to be able to pull and work on any of the hardware and makes life a little bit easier. Also, I should mention, these are a little bit wider racks than normal as well. So these are the 30-inch wide racks, not the standard 24-inch wide racks And again, part of the reason for that was because of the liquid manifolds and the cooling in the back. We need a little extra space to fit everything in. Here's the layout of the system. So when you're talking about a system like Frontera and the scale that we're looking at, we were doing the direct liquid cooling. So of course we had to take into account being able to provide CDU cooling. So when you look at one of the rows, the light green is the compute racks. So we have 30 racks in 2 rows and then 31 racks in the 3rd row. And in the ends and in the very middle, we have our cooling CDUs. We only need 2 CDUs to be able to cool the entire row of hardware. So we have some redundancy. So if we need to take one out of production to do some maintenance or some work on it, we can. And it provides plenty of cooling. We have plenty of overhead in terms of capacity with these CDUs. So we're not driving them too hard all the time. They've worked pretty well. They've been able to provide all the cooling we need. Oh, and on the backs of the racks, you'll see these little blue. Those are the chilled doors on the backs of the racks as well. The orange actually represents the core switches. I'll get into those here in a few minutes about when I start talking about the Mellanox network. But they're also liquid cooled. So we do have to have liquid cooling connections under the floor. We were lucky in one case that our data center already had a chill water line running underneath what used to be the old Stampede I hot aisle. And we were able to tap into that chill water line to feed the 3 CDUs on the end and in the middle and on this end as well. So, and then we needed an additional 6 connections because each switch has its own CDU for liquid cooling. So, so those of you who are moving into the data center design and system design, with the power increasing in the sockets and the designs of the racks that we're seeing moving forward, liquid cooling, some form of liquid cooling is really going to be required. So keep that in mind when you talk about facilities and design. I think we have a little talk this afternoon where we'll discuss more about facilities on that. So Frontera has been, like I said, 2019 has been very, very productive. With late 2021, we did the latest round of upgrades to CentOS 7.9. We also upgraded to Mellanox OFED 5.4.1. We've been trying to keep up with most of the software stacks and make sure that we stay up to date. Recently, a poll kit vulnerability was released and announced, so we had to very quickly roll out that on the system. So we do try to keep up to date, but I have to say it's a bit of a challenge because we want to make sure we don't break anything, and being able to test and confirm that we don't break anything prior to rolling out a bunch of updates is challenging. So we do typically carve out a small subset of nodes that we do an upgrade on and try to do as much testing as possible before we roll it out to the full system. We also upgraded to Lustre 2.12.6 client. We actually have stumbled into a couple of bugs with the latest 2.12.6. But there are some patches out there, so I am running a slightly patched version. The most recent release of Lustre, actually, we have one application we're still able to trigger a weird bus error with that we're still trying to identify, but debugging it has been challenging. We also installed and added the Intel One API compilers for users to start testing with. It has been our experience so far that they haven't been able to provide the same level of performance that the previous generation of Intel compilers have provided. So we still keep the default as the previous Intel 20 compiler versions. They are aware of this, they're working on it. They just haven't been able to get all of the enhancements and optimizations from their baseline compilers into the One API stuff as near as we can tell. So it's a work in progress. One big thing that we started with Frontera, and something that NSF has been very enthusiastic about, is what we call Texas Scale weeks. This is where we actually take the entire system and we do nothing but let one project group every day have access to the full system. And the goal here is really to push the boundaries of what applications can do, see where their weaknesses are, and hopefully if they've got a science problem that they want to try to get solved at scale, where they can't necessarily run it at smaller scale, we can give them the full system and then they can run for 24 hours continuously to get their results done. This has been extremely successful. During production, we typically can run up to 2,000 node jobs, no problem. And that's a quarter of the system. Those tend to work very well. But when you get up to the 4,000 node jobs, that's draining an awful lot of resources to be able to run on the system. And we prefer to do that, if possible, during these Texas scale weeks. Number one, so that we can have staff available to help debug and troubleshoot issues should they arise. And two, we're not fighting the queues and every other user that's trying to run on the system that could be potentially, impacting the file system, causing problems on the network. So right now we're scheduling these about once a quarter. So once every 3 months, we do these Texas scale weeks. We've had about 15 different project groups go through it so far. Some have done it multiple times. Inevitably, we do stumble into some kind of issue when people try to go to full 8,000 node runs. And it's been very helpful for us to fix MPI problems, determine weaknesses with file system issues at scale, figure out different techniques for being able to launch and run at scale. And again, this is really preparing these users for the next generation of the exascale systems when they become available. We want to make sure that the applications and the libraries and all the pieces of software are available to at scale. So we're going to continue this. In fact, we have another one of these scheduled in April. Our allocation period ends at the end of March, and we're trying to burn through as many of the allocations as users can. The system's been very busy recently. And we've actually completed more than 4 million jobs on the system since the era of production. So, but again, Frontera has been great. There have been some operational challenges. When you look at these systems, just the sheer scale, keeping up with hardware issues. We inevitably have nodes every day that some throw a warning with ECCs. You see these in the system event logs, or we stumble into some other system crashes. Some of them have been caused by leaks in the compute nodes that have caused some interesting crash behaviors. But yeah, keeping up with this is challenging. And it's not that it's hard to fix them. It's just that the scale and the number keeps the staff quite busy in terms of keeping the hardware repaired on the systems. And this is actually even more important during Texas scale days, because we want every node to be up and running and available. And if we have something go out like a switch or a node or anything, that we try to get it back as quick as possible so users can use all the resources. The other really operational challenge for us is just the large number of users, and inevitably they cause some kind of problem on the shared resources. And these are like the file systems, where they overwhelm the file systems with requests, or they suck up all the bandwidth, and their job is doing nothing but chewing up all the bandwidth to the IO and impacting other users who are trying to use the file systems. Similarly for the network, we do have some cases where some applications can really dominate and cause congestion on the InfiniBand fabric. And even on the logins, users aren't supposed to run on the logins. They're designed for compiling, submitting your jobs, managing your files, and so forth. Inevitably, somebody will launch an MPI job on the logins, and we have to go track them down and tell them to stop and quit it. The policy that we try to make sure that our users understand is, look, the system is available to lots of different users, and it's shared by many users. And the general goal is, one user shouldn't impact what every other user is doing on the system. And inevitably, when we go to the users and say, hey, look, you're impacting other users, you wouldn't be very happy if some other user was causing your job to run slow, or causing you to have to not be able to get access to your data or get file system errors. So usually once we get them to agree and understand that policy, then they tend to work with us and help make sure that the system runs effectively and efficiently. I mentioned cooling leaks. We've actually had some issues with cooling leaks inside the compute nodes. And these are actually leaks around the cooling blocks themselves. The downside now is we get no notification until the node typically crashes. Now we have leak detection under the racks and around the racks and under the floor for any potential leaks in the cooling system at that level. But inside the nodes, we have no available monitoring. The good news on this is Dell has fixed this, and I know Cool IT as well, with their new cooling loops that they actually have monitoring and notification built in, so they will detect leaks. So for future systems, this shouldn't be as big an issue. But we have stumbled into a handful of nodes that have had these leaks, and the fluid is an ethylene glycol solution, so it's like green antifreeze. And when it gets on the computer parts, it's extremely caustic, and will just totally destroy the motherboards and CPUs if it leaks into the CPU socket. So big operational challenge for us, and what we probably spend 50–60% of our time is troubleshooting errors. Whether it's a user trying to run an application and getting some seg faults or some system crashes or some weird messages, and ensuring that the system remains performant and stable. We can't have a loss of performance. So we did do a lot of regression testing when we do upgrades to make sure we're not losing performance. The good news is it seems that with newer kernels and newer libraries and stuff, we're actually seeing performance slightly improve with every generation of software update. So that's good news. So we're not seeing any fallback, but it's something we keep our eyes on very closely. And of course, I mentioned the Lustre client updates. We're actually working with DDN right now to do some debugging and collect some stack traces of the latest DDN client. Well, it's actually even in the Lustre open source client. We've also noticed that the same bug is there, but we haven't been able to reliably reproduce it. And this is challenging when you operate these systems, especially at scale.
Hey, Tom.
Any questions on Frontera before I switch gears and go into Lone Star 6?
Hey, Tom.
Feel free to jump in. Sorry, go ahead, Keith.
How many people do you have doing hardware break fix on Frontera?
So it's cycled between about 3 guys right now. They actually have some responsibility on helping out on other systems like Lone Star 6 and Stampede II. So we can kind of move people around a little bit. One person is solely dedicated to doing nothing but compute hardware repair on Frontera. The other 2 they help out depending on when things crop up. And if we have a system maintenance and we know we need to do a lot of work on the system, they'll typically help come in. But yeah, I'm looking at maybe increasing that staffing level. But it's a bit challenging because we have limited NSF funding to pay for people.
So how
Quick
many?
question: have you looked at? Sorry,
Go ahead,
I was going to say, have you looked at Arbiter 2 for policing your login nodes?
We've been trying to figure out some things. We have our own little tools that we've written to monitor when people launch MPI run. In fact, if you actually type the MPI run command, it's a shell wrapper script that says you're not supposed to run it on the logins, but users inevitably figure out how to work around that and run the actual executable. But yeah. So you said Harbinger was what it is?
Arbiter 2 out of Utah. They run that. They designed that for their login nodes to basically anybody who's using. You get the whitelist processes, and then say, these processes are good, and everything else that uses a lot of CPU time, throttle it down using C groups.
Yeah. Well, inevitably, it's the people running Python scripts on the logins that are a problem, and unfortunately, we have to let Python.
And it will catch those as well.
Yeah,
it will catch those.
Yeah, so what we look for is we actually look for processes that are accumulating a lot of time at 100% CPU. And if they do it for more than about 10 minutes, we get email notifications. So, so we're able to identify and find them. But yeah, that's a good idea. I'll look into that Arbiter too. Keith, you said there was another question?
Yeah, there's several, Tommy. Let me run around.
Oh, okay. All right.
You're the first one.
So you're running Rails 7.9. What's stopping you?
Well, yeah.
Sorry, CentOS 7.0. What's stopping you going to 8, or what's your plan?
Mainly because they changed the line of CentOS 8 is not really an upgrade path for us now. So it'd be a pretty big transition to switch over to Rocky. We probably will at some point later this year switch it over to 8. The thing is it's a bit challenging, and inevitably we're afraid about breaking existing stuff that users are already running. And that's one thing we want to make sure of is that we don't break, glibc compatibility or something like that with existing applications. You know, and when we deployed it, 8 was just coming out, but it was too new. You know, we don't like to use the 8.0 or 8.1 versions of releases, you know. we like most of the problems to try to get shaken out. So when we deployed Frontera, we actually deployed, I think it was 7.7 at the time, a couple of years ago, or actually almost 3 years ago when we started deployment. So so we've kind of stepped, and they still have long-term support for that line. Inevitably though, we're seeing that most of the new software is going to 8. And if we want to keep up to date with and keep testing some of the newer hardware, we're going to have to move to 8 on Frontera. I don't expect to upgrade Stampede 2. Stampede 2 will stay at 7.9 for the time being. It only has about another year of life.
Could you share about your cooling system leaks in compute nodes? What are the challenges you are facing, and what you have done so far to resolve those issues?
Yeah, so right now we're actually working with Cool IT to determine what's going on and why these are leaking. It turns out that most of the ones we sent back for FA actually have been factory manufacturing defects that have caused these leaks. The main concern and challenge from our point of view is the fact that we don't typically see that a leak has occurred until we open the node up for some type of problem. And inevitably, the problem that we normally see is that the node has crashed with some kind of voltage P fault, some kind of error, machine check event, something weird has happened on the node. And when we go to look at the hardware, you can see that the cooling fluid has leaked into the hardware. The good news is we typically can catch it before it gets outside of the node. We have had a couple of cases where there's been a little bit of leakage down to the nodes below that we've had to clean up. But we've been lucky enough to be able to catch it. But moving forward, I'm pretty sure the vendors have figured out that they have to have leak detection on the nodes themselves. And I know that the stuff I've been looking at recently has it all built in. So.
Thank you.
Interested to know how you manage your SLAs with your partners. You have people there on site that probably do your commodity replacement, DIMMs, hard drives, but what's your approach to SLAs? Do you look at the overall, how many nodes are available, and what's the response time? I'm really interested in knowing how you manage that.
Yeah, that's really one of the big things. The good news from our point of view is we don't have any direct SLAs with our users. They get the cycles for free from the National Science Foundation for the most part. So they really can't complain. However, we do have specific uptime requirements and availability requirements and job success rate requirements for NSF that we have to meet. From our point of view, they're relatively low bars though. They require us to have 96% uptime and availability. And we've actually been achieving about 98.5, approaching a little bit towards 99 this last year. And normally most of the downtime recently has just been system maintenance time, where we've had to take a day or two to do storage firmware upgrades and so forth. Tracking the job success rate is harder. So we have to track, when node failures has caused jobs to fail. But if a job fails due to a user bug, or they're testing and testing something, those are much harder for us to determine if it was a system problem. So right now we only track jobs that failed due to system issues and track that percentage. And again, we have a 96% job success rate. We're at a well above 99% job success rate on the system.
So do you look at that?
So we're a little bit flexible on that. Yeah, go ahead, sorry.
I was just saying, do you look at your SLAs and overall how many overall nodes available in the system?
Yeah. We do track how many nodes are out as well. The good news, even though we have maybe 10 or 15 nodes out of Frontera, it's a very small percentage. It's a fraction of a percent.
And
we have 8,000 nodes.
What's your SLAs with the Dell?
So for Dell, okay, so on the hardware, we have next business day for pretty much all the hardware. And so what we have is we have a parts locker. We've negotiated and pay for a parts locker on site. And so my guys do all the hardware repairs themselves. Sorry, I wasn't clear on that. We actually do all the ECC, DIMM replacements, CPU replacement, clean up the system leaks and so forth. And we just pay Dell to provide us a parts locker. When we need a new CPU, we scan it out of the parts locker. They drop ship us a part that shows up the next business day.
I'm guessing they're not giving you GPUs to store in there either.
No, yeah. we don't have that many spare GPUs. That one, we do have to take the node out of production for the day to replace it, should we have a GPU to replace. Yeah, we had to convince them to give us a few more processors in the parts locker, especially early on when we were going through them more frequently. But I think we only have like 5 or so in the parts locker at any given time.
And what was that?
Yeah, those expensive parts are hard.
Last question. What was that node leak thing that they put on in Cool IT? Because we just put in some direct to chip systems, so I want to hit them up for whatever they put in for node leak.
So hold on. I actually have an example of one in my office. So these are what, I'm not sure if you remember the cooling blocks in that picture I was showing, but these are the cooling blocks they're using now. And what they have now is they have these capture things on them where they capture the leaks. And then they have a little monitoring cable that plugs into the motherboard so that the motherboard gets notification. These can't be retrofitted to the old nodes, unfortunately. But if you have a new node that has a motherboard that has the fitting for it, these are what they're using now. So yeah, I just happen to have one in my office because they were dropped by with one of them to show us how they fixed the issues we've stumbled into.
Okay, we'll be sure to follow up. Thanks.
Okay. Any more quick questions? I can talk for hours, so.
Yeah, Jonathan from BP here. Just a quick, going back to the RHEL thing. Did you say you actually decided on Rocky, or is that something you're still exploring?
So that's actually the next system we're going to talk about is Lone Star 6. We actually did deploy Rocky 8.4 on Lone Star 6. We've stumbled into some, issues, especially updates, and we're not sure we like the way that they're doing their updates because it's not the way RHEL and CentOS has done it in the past. So it's a bit of a challenge. I'm open to suggestions. We tinkered with Alma Linux.
That's what I was going to ask about. Yeah, I was going to ask if you guys had done that.
And it, we didn't see it much different than Rocky. We know Greg Kurtzer pretty good because of his Singularity days and some of the work he's done, so we opted to go with the Rocky at scale. But I'd be curious about Alma experiences if you stumble into anything or issues. All right, let me jump forward into Lone Star 6. I'll rush through this since we're already running a little late. But so Lone Star 5 was our Cray XE40 system that we had, but unfortunately we had a hardware problem on a couple of the cabinets that accelerated our retirement schedule for Lone Star 5. So we had already been planning for Lone Star 6. We had been working on getting contributions from UT System and UT Austin and collecting money from the various partners that we have. But we did have a bit of a fixed budget on this one. So it's, we were targeting about $8 million worth of a system, but we wanted to obviously make sure we have options to be able to expand in the future. We looked at different processors in this case, and at the time we were looking at the deployment, the AMD Milan processors had just been released and were really given the best price performance option when we compared it to Intel and other GPU systems. This system itself, we did put some GPUs in. We got some of the latest NVIDIA A100 GPUs. However, most of the users of the UT-based systems, they don't typically leverage the GPUs as much. We do have a few machine learning folks that are using them and some molecular dynamics teams that like to use them, but a lot of the applications that our local UT researchers have are homegrown applications that they haven't ported into the GPUs. So in this case, we were, again, constrained on space and power and cooling limitations. We had some space where we had some air-cooled racks, but we also had areas where we couldn't really get much cooling in, and we had to either opt for some direct liquid cooling, immersion cooling, or some other approach to cool the nodes. So we did a mix in this case, and we evaluated, cost and scale of the system. And in this case, we went with a GRC immersion for the most of the nodes in the system, 336 of the nodes. And then we have 200 regular air-cooled 1U nodes, and then 40 nodes that are configured to be able to hold accelerators. Right now, 16 of those nodes have the A100 NVIDIA GPUs in them. We also had just recently got some AMD MI200s that we're going to put in some of them. And we also have some NEC cards as well, that some accelerator cards that we're testing. that we want to put in these boxes. These boxes are pretty impressive. They have 120 cores per node. Again, power. Power is really a big issue. You know, we're talking about 225 watts of socket. When you look at these nodes and you're running on these nodes, it's almost 800 watts for the whole node. In fact, I think when we measured some power on these guys, they actually go up to about 820 or 840 watts each. So you do need to make sure to account for that when you design your racks to make sure that you can provide enough cooling. And again, it's one of the reasons we opted for the immersion. You can get a lot of density in a pretty small space footprint and not have to do a lot of retrofitting to provide liquid cooling. And unfortunately, the Lone Star 6 system wasn't a big enough scale to justify the similar direct liquid cooling that we do on Frontera. You know, if we had maybe a couple of thousand nodes, then the direct liquid cooling becomes a little bit more cost effective in terms of the overall cost for the system. Again, it's a Mellanox system. This is all full HDR. So since we have PCI Gen 4 on each of the nodes, we did full HDR to each of the system. In this case, we did only top of rack 1U switches. We were able to do everything. When we looked at the 40 port switches and looked at the core, we opted for 24 nodes per switch and 16 uplinks. So that means we have a little bit of oversubscription on the fabric, but again, for this system of this scale, that was not nearly as much impact for us. The users typically don't run, you know, full system. In fact, most jobs probably are on the order of maybe 4 nodes, maybe 8, because that's you're already getting into almost 1,000 cores at that point. So again, we have Ethernet, but pretty much Ethernet is really only for management and shooting of the node. So here's what one of the compute racks look like. This is the air-cooled racks we designed for 25 kilowatts of power. It's 48U, regular width, standard depth racks that we would normally use everywhere. We also put our 2 storage racks and management racks and similarly. In this case, you know, we have 1 InfiniBand switch per rack, and that lets us connect to the 24 nodes in the rack. So again, you know, we did lay out how many nodes in the rack based on switch port count. Of course, we routed all the cabling so we can hop swap everything. I did want to point out the 4 nodes at the bottom are the nodes that we've actually allocated for accelerators. Oh, sorry, hold on. So those nodes, we only have 16 of them populated with the A100 GPUs. We are doing some Giga IO composability work with some of those nodes. We're also, like I said, putting some AMD and NEC cards in those nodes as well. One important thing we went here is we've really started to move to high voltage, high amp feeds for our PDUs in the racks. And this really helps us reduce the number of circuits that we have to run to the racks. So in this case, we feed each of these racks with 2 60 amp 3-phase circuits on them. The immersion tanks are interesting. We've been working with GRC for several years doing some immersion cooling with some GPU-based systems where we have you know, the regular RTX cards just in mineral oil. In this case, when we looked at the cost and the designs, we realized we could get the density out of the GRC for not as much cost as a direct liquid cooling. So we deployed 4 of the racks. These 4, there are 4 racks in the 1 tank there, basically connected by the pump and the heat exchanger. Each rack is capable of 80 kilowatts, and when we configured them, we actually put about 65 kilowatts of power in each of the racks. It does require 5 60 amp circuits per tank to be able to run that. And it's a bit challenging because you're limited in space into where to get everything into the tanks. And even the PDUs, which go up here with all the cable management, just being able to route everything in the tanks was a bit challenging. So we had to work with the GRC team to work on the deployment. So on the left-hand side, you can see the nodes actually in the mineral oil. So you can see that they're all contained in the mineral oil. And the tanks are designed so that there's an inner tank, and then if there should be a leak or any spillage, there's actually a secondary containment around each of the tanks as well, so that you can contain all the oil. Based on the node density and the amount of cabling, though, you can see we had to cram an awful lot of cables into a very small space. And you can see there's 4 PDUs here. We actually have a PDU mounted also in the middle of the rack here to provide power. The InfiniBand switches are mounted on the sides of the racks here. So you can see 3 of the switches here. We have all the cables routed into there. And the GigE switches are also mounted behind the InfiniBand switches here on the sides of the racks as well. But once everything is put together and self-contained, you can then wrap it and make it look pretty. So this is our new Lone Star 6 tank that we just got the wrap on recently. I think Dan showed this probably earlier in his keynote talk earlier this week. But that tank contains 336 nodes. And if you notice, it only takes about 8 racks worth of floor space. So if we had to do the 336 nodes, that would have been 15 racks of air cooled if we would have done it. And we just wouldn't have really had the floor space to pull it off. We do also change a little bit on this one. We went with BGFS. This is our first foray into running production BGFS systems. This is actually a configuration from Dell. And we work with the Dell team to do the deployment. They actually did all the deployment with our guys kind of shoulder surfing. And then we went through and made sure that we understood how to manage and maintain it. Again, the system has access to Stockyard and also it has access to our Corral data repository file system as well. In terms of software stack, here's kind of the building blocks of everything. I'm going to accelerate a little bit because we're running out of time and I want to get to the Stampede II updates. But again, we did Rocky 8.4 on this one. We've got the latest Mellanox OFED 5.4. We do run BGFS and Lustre. You can run both of them on your compute nodes as clients. And we're still using Slurm 20 for our scheduler on each of the systems. We do support containers. Singularity and Charlie Cloud are our preferred containers of choice. We haven't moved to Docker yet. And we know that they're working on improvements in Docker to allow it to run in user space solely. But for now, those are our 2 containers that we support. Of course, we build a whole bunch of libraries on top of all of this using modules and LMOD to manage all of the user software environment when they log on the systems. And we try to keep things consistent across each of our systems. So if you go to Stampede II, Lone Star 6, or Frontera, it's going to look very similar from the user point of view. Now, from the AMD point of view, we have found that the Intel compilers still seem to provide the best performance overall. However, we always support multiple compilers and try to support multiple MPIs on each of the production systems where we can. This allows us to really determine if it's compiler, MPI, or application related issue. Provides us an easy workaround in case we do stumble into issues in one of the compiler or MPI stacks. And the nice thing is the MPI, Intel MPI and InVapid2 are ABI compliant. You don't actually have to recompile your code if you want to switch between them. As I mentioned, we do find that Intel is most performant. We do have versions of the AMD and NVIDIA compilers available, but we haven't built all the libraries and software tools and applications for those compilers, because again, we typically find that the Intel one still provides the best overall performance. I mentioned the libraries. We actually support a fair number of libraries on the system and applications. It's based on user demand and requests. If users want a piece of software and we see it's pretty readily available and widely used, we will deploy it onto the systems. The HPC staff typically compiles all the application and library software and then hands it over to the systems team. And then it's our responsibility to make sure it gets deployed on all the compute and login nodes and consistent across all the systems. Again, we use module files to make a consistent software environment and still use local disk where we can to avoid impact on file systems. SSDs, 480 gig SSDs are relatively cheap now, so it doesn't cost that much to put in there. And we have been able to leverage it where users can use the local /temp space for IO if they don't need to use the shared file systems. And that actually, we've used that in many cases where we've had problems on users doing too much IO to the shared file system. I mentioned LMOD, I'll skip over this. I did want to show you a little bit about scaling performance in comparison to Frontera. So the AMD nodes right now are providing about a 1.3 to 1.5x speed up compared to the Frontera node. And this is just an application scaling up to 64 nodes on the system. And one thing I did want to point out is you get very good consistent performance, and this is using 8 tasks per node for the top blue line. You get 16 tasks per node, still doing pretty good. 32, you notice you're not getting full kind of performance decrease that you would expect. When this application hits 64 cores per node, it really has saturated the memory bandwidth. And so you don't get that much more performance going to 128, but you still get a little bit of benefit of using the 128 cores. One thing we have found with the AMD nodes is to really get the best overall performance, you need to leverage all the cores and take advantage of it. And it is challenging for some of our user applications that, you know, they weren't designed to run on nodes that had 128 cores in them. And so a lot of them are still trying to scale up and figure out how to use all the cores. And because of that, we're actually looking at potentially divvying up and putting virtual machines on a subset of nodes so that we can carve the nodes into smaller nodes. We try not to share nodes. We've had problems with users filling up temp if we do share nodes. We've explored using some C groups and everything, but it's never quite worked as well. So we're moving more to putting virtual machines in a subset of nodes so that if a user only needs 16 cores and 32 gigabyte of memory, you know, we can carve that out and let them run there and charge them at a much smaller rate than we do for a full node. Again, I mentioned the composable infrastructure. We just got some Giga IO hardware, just arrived. We're working on deploying it and installing it. Maybe I'll have some updates for that, hopefully next year. If I don't, then it wasn't successful. So Stampede II, we actually still running this as a workhorse. I'm gonna jump through some of this because we did take some of the KNL nodes out. And what I really wanna get to is discussion on the current status and latest additions to the system. So NSF realized that, you know, they don't really have any big production systems available to support the large number of cycles that are consumed by the research community every year. There's been a lot of new smaller systems that have gone out, but there haven't been any big ones. So because of that, NSF decided to extend operations for Stampede II for another year. And to augment the existing system, they actually allowed us to purchase some new hardware that I'll describe on the next slide. We did recently also upgrade Stampede II to the latest CentOS 7.9. We're running an OmniPath on Stampede II. So we did upgrade to OPA 10.11. Again, tried to do as much regression testing and confirming that we didn't break anything during the upgrade. Lustre 2's 12.6 Cray client, in this case, we actually did have to apply an additional patch to LL-Lite mmap-C. This is due to we have applications that will get hang basically, and you can't kill them. And they get stuck in an input stack trace. You can look at the stack trace and you can see it's trying to do an input function call. And we've had multiple applications to be able to trigger this. And there is a LU patch and fix out for you. If you are seeing this, I can point you to the specific patch that's available to fix it. Stampede 2 has been a real productive system, more than 9.2 million jobs over the life of the system so far. And right now we're actually taking very few system maintenances. You know, when we get late in the life of the system, you know, we don't want to do a lot of updates or changes because it's just running in production. So right now we're averaging about 2 or 3 a year in terms of system maintenances. And that's mainly just to get updates and new application software deployed onto the system. But more importantly, we did add some Dell R650 nodes, and these are the brand new Ice Lake processors. And these have shown some very interesting performance. You know, the big thing from our point of view is they've added another memory channel to the socket. So instead of getting 6 DIMMs per socket, we're now doing 8 DIMMs per socket. So now that's giving you an additional memory bandwidth, plus the memory speed is increased to 3,200 megahertz memory. So now these nodes have 80 cores. So these are the 40 core processors, 80 cores per node. We did reuse our existing infrastructure. So one of the things we leveraged is basically we pulled the old KNL nodes out of the racks, pulled the OPA cards out of those nodes and put them into the new nodes and put the nodes in the racks. So we replaced, for every 2 KNL nodes, we put in 1 Dell R650 node. And we had enough power in the racks, ended up only putting 28 nodes in each of the racks. And that ended up being about 25 kilowatts of power as well. These racks can support up to 30 kilowatts of power for cooling. If you've experienced on the Cascade Lake, we're seeing about a 1.4 to 1.5x speed up of most applications compared to a Frontera node. And it's interesting because we are seeing some applications that will do better on the AMD node using the 128 cores. But we also have a few applications that do better on the 80 core nodes, especially those that are more frequency sensitive. It seems that the Intel processors can certainly ramp up their frequency a little bit higher than maybe the AMD ones can. So, but it is application dependent. So, if you are running some specific applications on your system, you should certainly benchmark and test the various processors because, one may be more well suited for your environment than others. One challenge from our point of view is like I said, a lot of our UT researchers and local users don't typically run at the scale that we see on Frontera. And so using 128 cores per node is challenging. And so that's why we're exploring other virtualization techniques on the systems. So, and with that, I wanted to leave a few minutes for questions. So if there are any other questions, Keith, you want to do your dance around the room?
I'll run around, Tommy.
Hi, Tommy. This is Johnny Allen. I appreciate the good stuff. Thank you. Quick question. When your team is deciding as far as the components are concerned, what are some of the factors that play a role to pick those, which compute nodes from which vendor or which storage?
Yeah, this is always the challenge, and something that we try to weigh a lot here is really trying to get the best performance for the widest range of applications for the price. We are very cost sensitive. We are an academic university. We try to get things at discount where we can. Our vendors like to joke, HPC for us means half price computing. And then we joke back, well, if we're paying half, that's too much. But it's a challenge. On systems like Frontera or Lone Star 6, we need a general purpose CPU. If you're running specific applications that, are well suited and accelerated by GPUs, for example, let's say we were running nothing but molecular dynamics applications, I would certainly focus on buying a system that was more GPU oriented. And focus. And, NVIDIA's made a lot of inroads in terms of getting applications and libraries built and running on the GPUs. And it's something we've been impressed with the amount of effort that they put into it. But our problem is that maybe only satisfies 15 or 20% of our user base. We have this other 80% of folks that can't leverage the GPUs, and they would be sorely hamstrung if they had to use just the CPUs on the nodes that had these, accelerators in them. So it's a challenge. And so, for us, we try to take our applications that we know that are widely used on our systems. We have some molecular dynamics, we have astrophysics, we have CFD, we have material sciences, we have quantum computing, QCD codes. We have a wide, diverse range of codes. And so we try to figure out, what's going to work best for that processor. Sometimes we have to rely on the vendor to give us accurate projections, because we're planning a system a couple of years out. It's like, well, do we really believe, A, they're going to hit that timeline, and B, is it really going to perform at the level that we think it is? So yeah, it's a challenge, and it's always based on the applications you're running. And if your shop is running a small subset of applications, figure out really what architecture is best suited for that, and then build up on that. And inevitably, we always start at the compute nodes as the building block, the first thing. Figure out what you're going to put in your compute nodes, then you can figure out, how many per rack, and what your network's going to look like, and everything after you figure that, and then your storage. Now, another thing we also try to do is when we look at designing these systems, we try to focus and spend about 75 to 80% of the budget for the system on the compute hardware. That's actually decreased some over time because the interconnect and storage has gotten a little more expensive. We like to keep this interconnect at about 10% of the system, maybe a little bit more, and then storage at about 10% of the system. And that, for our user community, has been a pretty good balance. Obviously, if you're dealing with a lot more data, I know the oil and gas companies have much bigger data sets than we typically deal with. You may have to buy more bulk storage, and that factor may adjust a little bit. So, but when we're looking at our systems, that's kind of where we try to budget different things. And it fluctuates a bit, but consistently we try to get more than 75% on the compute, because then we feel like we're getting the most bang for the buck. Okay.
Thank you.
Thanks, everybody. Hopefully it was useful.